자, 오늘은 일단 해석학 먼저 할게요. 해석학을 할 건데 저번 시간에 해석만 했으니까 이번 해석학은 좀 길게 할 것 같습니다. 먼저 우리가 배웠던 케이스셋, 케이스들의 케이스들은 약간 이런 거예요. A가 RK의 부분집합이고 어떻게 되겠노? 네, 케이스셀의 정의입니다. 근데 여러분 이 말하는 건 every 케이스셀이 컴팩트라는 거예요. 그러니까 뭐 직관적으로 말씀을 드리면은 이걸 왜 하냐면 가운데 케이스가 그냥 박스거든요. 박스예요. 직사각형인데 직사각형을 일반화한 건데 어떤 바운티드 셋이 직사각형 안에 들어가겠죠. 그쵸? 그런데 그 직사각형이 컴팩트해요. 그러면 이 케이스는 당연히 유클리디안 스페이스 안에 있으니까 매트릭 스페이스 안에 있는 거죠. 그래서 케이스 안에 있는 어떤 클로즈드 셋은 컴팩트가 됩니다. 그러므로 이 세어럼을 통해서 우리가 유추할 수 있는 게 closed and bounded set은 closed set and bounded set 아니 closed and bounded set in Euclidean space is compact 라고 주장할 수 있어요. So let's study the proof of this theorem. Let I be the case set listing all point I I is a set of all x in K that there exists AI and PI and put delta A and the norm, the distance between x and y is smaller or equal to than delta for all x and y. Right. Okay. 음. For example, if Kate is 2, we can understand these statements by this figure. Any point in this box any 2 points in this box have a distance is smaller than delta. Okay, let me see. Both add there exists open cover G alpha of I, which contains no finite subgroup of I. In this assumption, under this assumption, if we find a contradiction, then we are done. Put bj as aj plus bj over 2. Like this. C2 and C1. Intervals aj, cj, and dj, bj. Tell me 2k pixel used by QR. Whose union is I. Then enlist one of these QI and be covered by any finite subcover of yeah. Otherwise, any QI can be covered by any finite some finite subcover of GR. Then this I is covered by a finite subcover of G alpha, the quotient of G alpha. So this is it is impossible under our first assumption. It is impossible. By this way, we next subdivide I1 and continue the process. Subdivide I1 and get I2, and then subdivide I2 to get I3. In this way, we get a sequence of IN. With the following properties. First, A, this sequence is decreasing sequence. Second, IN is not covered by any finite subcorrection of G alpha. Third, if X is in IN and Y is in IN, then the distance of X and Y is smaller than or equal to minus E minus N C theta. Right. IA, you know that mm, um, 2.39, there exists point X star which lies in every I1, IN. You think that this theorem 2.39 is not handled in our lecture. It is simple cor simple corollary of theorem 2.38, which we have learned. So, to read the proof of theorem 2.39 is a homework for you. The proof is simple. And for some alpha, X star is contained in G alpha. Why? Because the collection of G alpha is an open cover of I. So I and X star is an element of I. Thus there is some alpha such that X star is contained in G alpha. Note that G alpha is open, so there exists a positive number R such that B R X star is contained in G alpha. If n is so large that this number is smaller than R. This is just application of Archimedean property. And a C implies only n is contained in G alpha. But this means this is a contradiction. Why? B says that IN, any IN is not covered by any finite subcollection of G alpha. But by A and C, we can conclude that on one IN is contained in one G alpha. One is a finite number, so it's contradiction. Thus we are done. Okay. The main idea of this theorem is to subdivide a K-cell uh, if there is a point x star which is contained in any IN, then there must be one open cover, no, open set, which is an element of open covers collection, such that x star is contained in G alpha, and for large n, IN is contained in G alpha, same G alpha. So by subdividing K cell, we can put each in is in one G alpha. Then this 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 box subdivided boxes are is contained in are contained in one cover G alpha 1, G alpha 2, G alpha 3. Okay. You know the sys e even if we subdivide the box and many time, this is finite many time. Okay. Thus, we can choose a finite subcollection from original open cover. That is main idea of this probe. One box, one open cover. One open cover element. One box, one element of open cover. Okay. This is we are done. Next theorem, the Heineberg theorem. Heineberg theorem. If a set E in Rk some one of following three properties, and it is the other two. A, the set E is closed and bounded. B, E is compact. C, every infinite subset of E has a unit point in E. You must be careful to that the large space in which E is contained is Euclidean space. The Heineberg theorem may be false in more general space. Let's study the proof of Heineberg theorem. E is bounded in Rk, then there exists a K cell I such that E is contained in I. I is compact and E is closed in metric space. So, and E is contained in I, so E is compact, right? So, so we are done from B to C. Let's see from B to C. Uh, this statement is followed by 2.37. So let me prove this theorem right now. If no point in no, no, settlement, if E is an infinite subset of a compact set K, then E has a real point in K. Why? Suppose not. If any point of K is not a limit point of E, then for any Q in K, there exists a neighborhood Q such that the intersection of VQ and E is almost singleton. Empty or singleton. If Q is in E, then the intersection is singleton. Okay? So it is clear that any there is no finite sub collection of VQ covering E, covering E, right? Because E is an infinite subset, so um, and the same is true for of true okay if E is contained in K. But this is contradiction because K is compact. Okay, we are done. Next, the last is from C is to show that it is true from C to A. Okay, it is a little bit long. Suppose not. First, if it's not bound, E contains point with with xn. The norm of xn is larger than n. N is for any natural number n. Let S a sequence of xn. S is infinite and has no limit point in K. Thus, the norm of xn diverges, so there's no point, no limit point. Hence, none in E plus C implied is bounded. YS has no limit point. the only point in RK. Why does S have no only point in RK? In figure, you consider this point more, more, more. Mm, the distance between xn and xn plus, or xn and xm for different n and m, will be large as n and m goes to infinity. As- uh, uh, Suppose there is a ring point of S, then any neighborhood of the ring point has non-empty intersection with S. But the distance between any two points of S is larger than some constant number. So there is no ring point of S. 그러니까, Next, if E is not closed, and there exists x0, which is a ring point of E, but not a point of E, right? For natural number n, there exists a point is n in E such that the distance xn and x0 is smaller than 1 over n. This is just definition of a limit point. Similarly, let S be the set of xn, then xn and S is infinite. Why? If not, If not, the distance between xn and x0 is constant for all finite for infinite remaining n, right? Then x0 is not any point of s, 아니, of xn. x0 is the end point of E. An assumption S has no. Just x has x0 is a mean point. S has no other mean point. Okay. Why? For if y by the triangle inequality, this is Archimedean property. This is followed by Archimedean property. This shows that y is not a limit point of S. Okay? Thus, S has only limit point x0 is set as, but this x0 is not a point of E. So This is contradiction. C. We can conclude that. Yes, we can conclude that E is closed. Well done. Let's study the next theorem. Weierstrass theorem. Every bounded and infinite subset of Rk has a ring point in Rk. Why? The proof is very easy. Very easy corollary of the theorem of this theorem. Every bounded set is contained in a K-cell, and K-cell is compact. If E is compact set, then any infinite subset of E has a ring point in E. In this case, the set E is a K-cell. Any infinite subset and any bounded and infinite subset of Rk is contained in a K-cell. So this set has a ring point in a K-cell. Because the K-cell is a subset of Rk, the ring point is contained in Rk. Okay. The proof, give it a done. Next, perfect set. Perfect set is the set is the closed set whose any point is a ring point of the set. In other words, the set E is perfect set if E is closed and any point of E is a ring point of E. Theorem 2.43. Let P be a non-empty set, non-empty perfect set in Rk, then P is uncountable. Since P is closed, P has ring point, so P must be infinite. P is infinite. It is clear that P is infinite set. Be careful that if P is it is not the reason of this infinite set. Sorry. Okay. Why P is the infinite set? P is non-empty, so P has an element of P is own element, and its own element X. By definition of P, X is a ring point of P. So P must have infinite elements. This is not the result followed by closedness. The closedness implies any ring point is contained in the set. If there is no ring point, there's no guarantee that the set is infinite set. So be careful. This fact is not followed by the fact P is closed. Okay? We must show that P is uncountable. So suppose not. Suppose P is countable. No. P by xn to zero xn. Let V1 be any neighborhood of x1 if V1 neighborhood. More specifically, V1 is one. Okay. We will use an induction argument. What Vn has been constructed so that the intersection of Vn and P is not empty. Okay. There exists element of Xn, right? Mm-hmm. Because this is not empty. This set is not empty. There is an element Xn in this set. Since Xn is a limit point of P, there exists a neighborhood Vn plus 1 such that when the closure of Vn plus 1 is contained in Vn, to Xn is nothing Vn plus 1. 3 Vn plus 1 intersection P is not empty. Right? Why? Because xn is a limit point of P, there exists a neighborhood W, okay? W, no. Any neighborhood of xn has the intersection with P, which is not empty. So there is W. Small neighborhood. Mm, it's Vn. Okay. And this is a P. There exists W. Any neighborhood of xn, W has intersection with P, which is not empty. Uh, uh, mm, okay. Then there exists an element xn plus 1. Right? Mm-hmm. Okay. Mm, prime Vn plus 1 prime is contained in Vn, and the closure is also contained in Vn, and the Xn uh, okay. Uh, let's see. Okay. This W is contained in first this W is selected by the closure of W is contained in Vn 1 and 2. The condition 2 and 2 is mm, because Xn is a limit point of P, there exists fixed W satisfies the subtraction X from W has intersection with P, which is non-empty, and there exists a neighborhood of X of W1 over Xn such that W W1 the subtraction W1 from W has intersection with P, which is non-empty, and W1 is contained in W. This is W. Maybe it's a closure. Okay? W 음 let n plus 1 and 2 and 3 are displayed. Okay. Right. Mhm. Okay. Right. Condition 3, Vn plus 1 satisfy our induction hypothesis and the construction can be proceeded. Good. Kn intersection PD and the intersection of the closure of Vn and P. Since the closure of Vn is closed and bounded, Vn is compact. Then Xn is not contained in Kn+1. So no point P or P lies in the intersection of all Kn, right? Because each Kn is contained in P, the intersection of all Kn is in P. It's contained in P. So this is empty set. But each Kn is non-empty. By 3, Kn is non-empty, and Kn is decreasing by 1. So by the theorem corollary, by the theorem, it contradicts to theorem 2.36, which we already learned. Okay, we are done. Plus P is uncountable. By this corollary, we can say any closed interval is uncountable. Thus, in particular, the set of all real numbers is uncountable. But 2.44, the control set. Control set is an amazing set which has nice properties. Which is contained in closed interval 0 to 1. Let E0 0, 1 remove 1/3, 2/3. 1, 1/3, 2/3. And E0 E1. And remove the middle third of this interval. And E1 2 3 on each interval we subtract the middle thirds of these intervals. To get the E3 and from En remove the middle thirds of intervals of En to get En plus 1 and put the sequence of En has these properties. En is the union of 2n each of lengths set E, which is all intersection of En, is called the control set. So by the theorem 2.36 is 90. Homework. So that he has no line segment. Homework. He is perfect. So that P is perfect set. 네. 어 음 네. is 음 오늘 수업은 끝났고요. 말씀드린 이 내용들 잘 숙지하시고 공부를 하시면 좋을 것 같습니다. 사실 오늘 다 베이스 토포로지 다 끝냈었는데 남은 내용이 이제 이 커넥티드 셋하고 패스 커넥티드 셋에 대한 내용이에요. 이거는 좀 이게 PMA 저희가 지금 보는 책이랑은 쪼끔 책에서는 쪼끔 대충 알려주거든요. 네, 그렇게 하기보다는 마스터되는 내용을 해서 같이 공부를 해 보는 게 좋을 것 같다고 생각을 해서 다음 시간에는 커넥티드 셋과 패스 커넥티드 셋에 대한 이야기를 해 보고자 합니다. 자, 오늘 해석학 수업은 여기까지입니다. 감사합니다.